All right. Wait, what? Okay, we're good. So this is the presentation for reinforcement learning for vision-based manipulation with Handy. And this is the group with the three of us. I'm Anthony, there's Ritesh, and Abdul Latif. So we've been doing this for the spring semester, and we're all graduate students in the OMSCS program. We'll talk a little bit about some of our goals for this project, and then we'll go into reinforcement learning with a custom OpenAI environment, the actual Handy environment, the simulation that we use to test the robot, and the interface between these two components. And then we'll talk about some of the future work. So our goals for this project are basically to figure out how to run Handy to move the basically to figure out how to move the arm towards an object in Handy's environment. And so what we'll do is we'll put a camera on Handy's end effector, and we'll use the end effector to pick up an object. The typical way that this is done is that there will be a fixed camera in the scene that's pointing towards the robot and its environment. But here we want to be able to do this movement without having a fixed camera and without having to do a calibration process that is fixed to a specific transform. So we'll be using deep learning methods to do reinforcement learning with Handy. There's a bunch of goals here, but this kind of boils down to three main goals in our project. The first is to create a custom environment for Gymnasium, which is the reinforcement learning API. The second is to create a ROS node to process image data that's coming out of Handy. And the third is to build a RESTful API for the RL agent, which puts together the simulation with the reinforcement learning environment. So as part of the semester, one of the things that we did in the semester was to do a little bit of literature review. And so one of the things that we did this semester was actually put together kind of related works for the project. And so this was one of the things that we've managed to do this semester. It was an interesting piece of work. So with that all out of the way, I'll hand things over to Ritesh to talk a bit about reinforcement learning with custom OpenAI Gym.
Thanks, Anthony. Guys, my name is Ritesh. I will go over the reinforcement learning part. Just a little background. Last semester, we were able to create an agent. I used an agent already available in the API, OpenAI Gym's API, and we were able to train an agent using one of the existing algorithms from the stable baseline libraries. And so natural continuation to that is this semester we want to create our own environment so that we can use our own Handy eventually to be able to control it through the environment. So I'm going to go through how to create a custom environment. So just a quicker on the OpenAI Gym. It's essentially a toolkit where you can play around with a lot of different reinforcement learning algorithms, and they provide you out of the box environments to try out. Some of them popular ones are the Cartpool, Fetch and Reach, Atari games, Space Invaders, and things like that, which you can go to the website and play and see how they work. And next question would be, why do we need custom environments? Is essentially if we want to have our own private simulation, then we will need our own environment because OpenAI does not have all of it, so we have to create our own. Can you go next slide, Anthony? So a majority of my slides are going to be describing how to structure your project to create an environment, because OpenAI API expects the directory structure to be in a certain format for it to understand so that it can facilitate the environment. In this case, we are creating an environment for Handy. And you can see that there is a top level Handy folder, and then there is a bunch of other folders inside it. Next, I'll just go over the details of some of these files. Most of the files do not have much content, but they are important for it to kind of work together. Yeah, you can go to the next slide. One of the files, the setup files here, basically we tell all our dependencies. the version of our environment. And in this case, I only had generation dependency. But if you had like pandas or Pygame or any other dependencies, any versions that are required, this is the place they would put in. And when the environment gets activated, the environment will automatically install all these dependencies for you, along with the current version numbers, so that it's ready to go. In the init file at the bottom, that one is needed for registration of the environment with OpenAI. Here is where you give the name. Handy, in this case, is Handy version 0. This is the name that you eventually call when you actually create an environment from the OpenAI, and you give it the name of the class, the initial class where the program will enter when you start running your environment. Yeah, go to the next slide, Anthony, please. This one is another init file. I mean, I have put paths for all the files in there. So just in case, there are multiple files with same names. So just be mindful of which file I'm talking about. This file has not much in here. This is only present to create a Python package so that you can import it down when you have an environment ready to do so. Next slide. This is the main one. This is the place where you actually do all the coding, which is needed for creating an environment. I have shown 4 main functions that are absolutely needed for environment to be created. First one is the reset and function of its method. This one basically resets the environment and gives you an initial position to start off everything with, right? So it cleans up everything from the background and just restarts your environment. Second one is the step. This is where basically you tell the environment, hey, this is the step to be taken. And the environment will go ahead and take the step and process the step and give you back the next observation from the environment. And third one is render. This is basically how you want to render. Usually people use a human rendering mode. There is some visual to look at so that you can kind of understand how the environment is moving around, how the robot is doing. But eventually you can remove that human environment and just let it run as is. Finally, it's the final method is close. This is where once the environment is done, you want to end the session, release some resources, close all the windows. If you're using Pygame, then you just quit Pygame and whatnot. So this is just the cleanup step, the tear down kind of step of the environment. So all of these are important. Yeah, so these need to be there. This file is not needed by the environment, but I put it in here. Once you have the environment ready, then you can use something like this to call the environment, to make an environment, to do the reset. And then you are basically entering into a true loop where you, in this case, I'm just sampling from an action space, but this can be actually coming out from an agent, right? So agent can look at the observation that you get from the reset state, and agent will say, okay, this is the observation, so this is the best next step to be taken. So it will return an action, and then that's the action that you give to the environment step function, and environment will take in the step, return a new observation, and you kind of go back and forth with that. And this is how the learning will happen eventually, and this is how the inference will also happen, right? That's what both the things will use essentially the same kind of an algorithm. So this is all about creation. This, if you follow the steps, I think the environment should be ready. And after that, it's all matter of you customizing your environment to your needs, training your own RL agent, and taking it from there. Yeah. So that's it from my side. Thank you. I'll hand it over to Abdul.
Yes. Hello. So I'll be talking about the Handy environment progress. Next slide, please. So the main goal is attaching the camera to the manipulator arm. And throughout the semester, I've tried different approaches on how to manipulate the URDF files. I will be discussing the different approaches of what worked, what didn't work. And later on, I started studying ROS, and I covered some of the concepts in later slides. So this was the initial work that we did, which was modifying the URDF file directly. But this was done, and it wasn't really integrated with the full environment. So there was no Gazebo plugins, no other integrations with Orvis present. Can you go to the next slide, please? And this showcases the initial attempt, which was inside your robot tag. In the URDF definition, we include the arm, and then we search for the link or the joint that represent the end effector, and attach the camera to that link. So this attempt has worked, but This approach directly modified the URDF, and it was not part of the larger Gazebo launch file. Next slide. I've tried different approaches by just thinking through the different tools that we have. So we have ROS launch files, we have URDFs. So I was like, maybe I could do it on the ROS launch file and do it sequentially. But then while going through the forms of ROS, first of all, ROS launch file does not guarantee that these things will be launched in sequence. And on a higher level, if you go to the next slide, when we do this approach, it actually creates two separate robot models. So whatever you're referencing across these two will be unidentified. Let's say the robot arm has link 8. It will not be present in the camera because they are actually separated logically. Next slide. The second attempt was to launch the first and then wait 20 seconds and then launch the second one. But again, that also didn't work because of the initial assumption that they need to be in the same composite model and not separated. Okay. So after that, I've realized that I have a gap in understanding ROS2 fundamentals. So I took a few tutorials around ROS and I've learned some of the fundamentals. So yeah, we can stay on the same slide. Okay, so we have the robot model description format, which is called URDF, and it consists of joints and links. And whenever you have joints and links, you think about motion. So we think about each link and how other joint and link will change with respect to it. And for that, we need coordinate transform, which allow you to define a base frame or reference frame, which is the word, and then you attach how the base would be attached to the word, and let's say another joint that is attached to the base, and how would they move. And mainly when we talk about TF, we talk about translation and rotation with respect to another reference frame. This next one. So whenever we look at URDF files, which have a binary tree, let's say, of links that are connected by joints, they are closely related to transforms, which are also a binary tree of frames that are connected by transforms. And at the beginning of this trees, either the links or the transforms, you would have the word, and then you would have your robot models and how they could be moved together. Next slide, please. Okay, so how could you combine your URDF, which describes your joints and links, with the current state of your joints? So let's say one of your joints has rotated or it has been translated. How would it be captured? So there was a component called Robot State Publisher that takes these two items as inputs, and it broadcasts as ROS topics the current states of your joints as transforms. So other robot systems, other ROS nodes can use them to accordingly act on them, either to move or just understand how the system moves. Next slide, please. Okay, so how would Robot State Publisher fit with Gazebo? On the larger picture, we would replace the manual input or a simulated input from joint states, and then link it to a plugin in Gazebo that publishes the joint states for the simulated physics model. Of course, this will broadcast the transforms. It will broadcast the robot description, the URDF. And then in Gazebo, there is also the spawner command, which creates that 3D model or the physics model in Gazebo. And of course, you can have many other plugins, such as the sensor plugin if you are having some observations in your environment, or some control input commands, which could simulate movements of the joint, and that will go back to joint states, will be published to joint states, and this loop just repeats. Next slide, please. Okay, so after the understanding, the next steps would be to build a composite model and then integrate it with what you have seen in the previous slide, which is the Robot State Publisher, and configure the proper plugins. Next slide. Yes, and that's it from my side. I will hand it over to Anthony.
Great. So I'll talk about the gymnasium interface, which is the piece that lies between the Handy simulation and the actual gymnasium API that Ritesh put together. So the goal of the gymnasium interface is basically to give the Python code that's going to be used for reinforcement learning an API that doesn't depend on all of ROS. So if you're building an agent for reinforcement learning, you shouldn't have to install ROS2 or ROS or Gazebo or anything. You should just be able to install the Gymnasium API and talk to the simulation over some sort of HTTP interface. And so the initial version of this last semester was a controller that was able to read from ROS topics and get the current state of the robot. So here we have a button, and if we click the button, we can get the current robot state, which includes the joints, the joint positions, and whatnot. But it didn't include any ability to actually send commands to the robot. And the simulation was still the simulation had to be reset on a new computer of mine. So through the semester, actually got a working demo of sending a trajectory command to the robot. So here we basically create an endpoint using Fast API, and this API is at /controller/trajectory, and by sending a pose to this this endpoint, we can use move it to move the arm into a location using this asynchronous endpoint. And so this actually works pretty okay. And there are some slight bugs that need to be worked out because of the service calls and related things that need to be done through ROS. So not all of the pieces have been plumbed through, but as a proof of concept on a new VM that I had set up on my computer, this actually surprisingly works. So there's as you know, here's a diagram of the high level overview. Really, this is going to be one REST API for one robot, and if we were going to increase the number of robots for simulations, we would actually create one environment that had multiple robots in it, which is a solution that would scale to potentially other simulation environments. But you could also imagine having one REST interface that talks to several backends. So simulations could live on other computers and not the computer that you're currently running on. So finally, just kind of what future work entails. There's still the complete integration of the camera that needs to be done to the Handy arm. There's still the integration of the gymnasium environment on Handy with the rest of the simulation. There's still learning a policy on the simulated Handy robot where you take images and use that to visually move the arm. And there's seeing what the policy would look like on the physical robot. Everything that we've talked so far has been all in simulation. And it would be really cool to validate the hypothesis that we can learn to move an arm towards an object using just a camera on Handy's wrist. So with that, that is our presentation for this semester's VIP. Thank you.